Hey everyone, and welcome to a deep dive into simulations. We're going to be looking at some really cool articles and notes about how we use these simulations to understand how systems behave and make predictions about
Well,
them.
it's kind of like having a virtual sandbox,
Yeah,
where you can experiment without having to worry about messing things up in the real world.
exactly. And today we're going to explore why these simulations are so valuable and the different types that exist. We'll even get into some specific techniques. It's like a crash course in how we use these virtual worlds to understand the real one.
And it's not just about complex scientific research or anything. We use simulations for everyday stuff like designing traffic flow or predicting stock prices.
Right. So before we get too far ahead of ourselves, let's start with the basics. What is a simulation?
Well, at its core, a simulation is basically just an imitation of a real-world process or system. Think of it like creating a digital twin of something. It could be a simple object or a complex system like a whole city.
So instead of, building a real bridge and hoping it doesn't fall down, we can build a virtual bridge and test its limits in a simulation.
Exactly. You can apply different stresses, simulate different weather conditions. You can even see how it would respond to an earthquake, all within the safe confines of a computer.
That makes a lot of sense. But to simulate something, we first need to understand what we call a system. Can you break that down for us?
Sure. A system is basically just a collection of interconnected parts that work together in a regular way. Your car is a system,
Yeah.
your body is a system, even like the ecosystem of a forest is a system.
Okay, so the first step in creating a simulation is to define the boundaries of the system we want to simulate, like what's inside, what's outside, and how do they interact.
Right. And everything outside the system is called the environment. And the way a system interacts with its environment is how we classify it as open or closed.
Okay, give me an example. What would be a closed system?
Imagine a perfectly sealed thermos flask. Ideally, nothing's entering or leaving the flask, making it a closed system.
Ah, I see. So how about like a bustling city like New York? You have people and goods constantly flowing in and out, information being exchanged. It's influenced by weather patterns and global events. That's got to be an open system, right?
You got it. And open systems are much more common in the real world, and also much more complex to simulate.
Okay, now I'm curious about the why of simulations. I mean, beyond the obvious safety and ethical considerations, why go through all the trouble of building these virtual worlds?
Well, for one thing, simulations can be incredibly cost-effective. Think about it. It's a lot cheaper to crash a virtual car in a simulator than a real one on a test track.
Yeah, good point. Plus, there's no risk of injury to a test driver in a simulation.
Exactly. And simulations allow us to experiment in ways that would be impossible or just impractical in the real world. Like we can speed up time, we can slow it down, rewind events, manipulate variables with ease.
It's like having a time machine and a superpower all rolled into one.
You could say that. But maybe the most valuable part of simulations is their predictive power. Like by understanding how a system behaves under different conditions in a simulation, we can make predictions about how it might behave in the real world.
It's like peering into the future, but instead of a crystal ball, we're using data algorithms and computational power.
Precisely. That's why simulations are used in such a wide range of fields, from predicting the spread of diseases to designing more efficient transportation systems.
It sounds like there's a whole universe of simulations out there. What are some of the main types we should know about?
There are lots of different ways to categorize simulations, but one common approach is to divide them up based on how they handle time and events.
Okay, tell me more.
We have what are called discrete event simulations, where the simulation focuses on specific points in time when events occur. For example, in a simulation of a bank, a customer arriving or leaving would be a discrete event.
So it's not about like every second that ticks by,
Yeah.
but rather about the key moments that change the state of the system.
Exactly. It's like fast forwarding through a movie and only stopping at the important scenes. Then we have continuous simulations, which use mathematical equations to model systems that change smoothly over time. Think about simulating the flow of air over an airplane wing or the growth of a population.
So it's like watching a plant grow in time lapse versus flipping through a photo album of key events.
A great analogy. And then there are Monte Carlo simulations, which use randomness and probability to model uncertain events.
Monte Carlo. That makes me think of casinos and gambling. Is there a connection there?
Absolutely. They're named after the famous Monte Carlo casino in Monaco because they rely on random sampling, much like rolling dice or spinning a roulette wheel.
So instead of trying to predict the exact outcome of a single event, Monte Carlo simulations help us understand the range of possible outcomes and their probabilities.
Exactly. This makes them super useful for assessing risk in situations where there are many unknowns, like financial markets or weather forecasting.
That makes sense. And you mentioned another type earlier, agent-based simulations.
Yeah. Agent-based simulations are unique because they focus on modeling the behavior of individual agents within a system. Each agent has its own set of rules and interacts with other agents and the environment.
So it's like creating a virtual ant colony, where each ant follows its own simple set of rules, but collectively they create complex patterns and behaviors.
That's a great way to visualize it. These simulations are particularly useful for understanding complex social systems, like how traffic patterns emerge or how crowds behave in emergencies.
Wow, this is fascinating. So we've got these different types of simulations, each with its own strengths and weaknesses. But before we dive into specific examples, can we talk about what makes a good simulation?
Absolutely. Building a good simulation is kind of like constructing a sturdy building. It all starts with a solid foundation, and in simulation, that foundation is the concept of block building.
Block building. Are we talking about Lego bricks here?
Not quite, but the analogy is helpful. It means breaking down a complex system into smaller, more manageable blocks that we can understand and model individually. Each block represents a specific part of the system, and by connecting them, we can recreate the behavior of the entire system.
Okay, so it's divide and conquer strategy for complexity. What else is important?
Relevance and accuracy are crucial. The model should focus on the elements that are truly important to the problem you're trying to solve and use accurate data to represent them.
So garbage and garbage outright.
Exactly. If you build a simulation of a plane using inaccurate data about its aerodynamics, it's not going to fly very well even in the virtual world.
And speaking of simplifying complexity,
hmm
you mentioned something called aggregation earlier. What's that all about?
Aggregation is about finding that sweet spot between detail and simplicity. It's the idea of grouping individual entities into larger blocks to make the model more manageable without losing too much accuracy.
Can you give me an example?
Imagine you're simulating traffic flow in a city. Instead of tracking every single car, you could aggregate them into lanes of traffic. This simplifies the model without sacrificing too much detail about how traffic moves through the city.
So aggregation is like zooming out on a map. You lose some of the finer details, but you get a clearer view of the overall landscape. But once we've built our model and run our simulation, how do we know if it's any good?
That's where verification and validation come in. Think of it as quality control for simulations.
Okay, so verification is about making sure the simulation itself is working correctly, and validation is about making sure it accurately reflects the real world.
You got it. Verification is like checking the plumbing and electrical systems in our building to make sure they're functioning properly. Validation is about making sure the building itself meets the architect's design and purpose.
So verification is about internal consistency, and validation is about external accuracy.
Precisely. We verify by checking for errors in the code, making sure the logic is sound, and ensuring the simulation behaves as expected. We validate by comparing the simulation's output to real-world data or expert judgment.
This is making a lot of sense. We've covered so much ground already, from the definition of simulations and systems to different types of simulations and the principles of building good models. I'm eager to dive into some more specific examples, especially that Monte Carlo simulation you mentioned.
Me too.
But let's take a pause here to give our listeners a moment to digest everything. When we come back, we'll explore the fascinating world of curing systems and see how simulations can help us understand those pesky waiting lines we all encounter in everyday life. Stay tuned.
Welcome back. I'm excited to dig into a specific type of simulation we talked about earlier, queuing systems.
Queues, those dreaded waiting lines we find everywhere, like at the grocery store or in traffic jams. Can simulations really help us understand and maybe even conquer these everyday frustrations?
Absolutely. While they might seem kind of mundane, queues are actually pretty fascinating from a systems perspective. You see, they emerge whenever the demand for a service outpaces the capacity to actually provide that service.
So it's a classic case of supply and demand, but instead of goods, we're dealing with services.
Exactly. And the relationship between the arrival rate, that's how quickly people or things enter the queue, and the service rate, how quickly they're processed, that determines how long the queue gets and how long we have to wait.
Okay, that makes intuitive sense. But how do simulations come into play here?
Well, instead of creating chaos by tinkering with real-world cues, we can build a virtual queue in a computer and experiment safely. We can tweak arrival rates, service rates, even test different queuing disciplines.
Queuing disciplines, what are those?
Think of it like the rules of the waiting game. The most common one is FIFO, first in, first out, where the person who arrives first gets served first.
Ah, the fair play approach we see in most lines.
Yeah.
But I bet there are situations where other rules apply.
You bet. Sometimes it's LIFO, last in, first out. Think about getting on a crowded elevator. The last people in are often the first ones out.
Yeah, that makes sense. It's not about fairness in that case, but rather the physical constraints of the system. Are there other interesting queuing disciplines out there?
Absolutely. We have zero service in random order, where it's anyone's guess who gets served next. It's like picking a name out of a hat.
Sounds a bit chaotic. Where would we see that in action?
Think of a raffle drawing or a lottery system. It's all about chance and unpredictability.
Interesting. What about situations where efficiency is really important?
That's where STP comes in, shortest processing time. This discipline prioritizes those who need the least amount of service time, making the queue move faster overall.
Like an express lane at the grocery store for people with just a few items. That's brilliant.
Exactly. By simulating these different queuing disciplines, we can figure out which ones work best in different situations, optimize resource allocation, and minimize those frustrating wait times.
This is eye-opening. It's like simulations give us X-ray vision into these everyday systems that we often take for granted.
And speaking of systems that are constantly in flux, let's switch gears a bit and explore another fascinating type of simulation model, the cobweb model.
Cobweb. Is this going to get spooky?
Not at all. Cobweb models are basically visual representations of how supply and demand dynamics play out in markets. They get their name from the way the lines crisscross on a graph resembling a spider web.
Okay, that's starting to sound a bit more familiar. I remember those supply and demand curves from economics class.
Yeah.
How are cobweb models different?
Well, while those classic curves show a static equilibrium, the cobweb model adds a dynamic element by illustrating how adjustments in supply and demand often happen with delays.
Delays? What do you mean?
Well, imagine a market for apples. Let's say there's a sudden increase in demand due to a new health trend advocating for apple consumption.
Okay, so everyone's suddenly craving apples. What happens next?
The higher demand leads to higher prices, which signals to apple farmers to plant more trees for the next season.
Makes sense. Farmers are responding to the market signals.
But here's the thing, it takes time for those new trees to bear fruit. By the time the next harvest rolls around, the market might be flooded with apples because all the farmers reacted to that initial price spike.
Ah, I see. So now we have a surplus of apples and the price drops.
Exactly. This lower price might discourage farmers from planting as many trees the following year, leading to a potential shortage down the line and pushing prices back up.
So we have this fascinating dance between supply and demand, with these time lags creating fluctuations and those signature cobweb-like patterns on the graph.
You got it. The cobweb model helps us visualize and understand these market dynamics. It reveals how those delays can lead to periods of oversupply and undersupply, causing prices to fluctuate over time.
This is giving me a whole new perspective on how markets work. It's not just a simple balancing act, but a complex interplay of forces with ripple effects across time.
Precisely. And that's just one example of how simulations can help us unveil those hidden patterns and dynamics within complex systems.
I'm already starting to see cobwebs everywhere. But let's not get too tangled up just yet. We've covered some specific techniques like Monte Carlo simulations and cobweb models. What other fascinating insights await us in the world of simulations?
Oh, there's so much more to explore. We haven't even touched upon some of the incredibly powerful applications of simulations in fields like medicine engineering and climate science.
This is getting me really excited. I can't wait to learn more. But before we get ahead of ourselves, let's take another pause to give our listeners time to process all this amazing information. When we come back, we'll explore even more fascinating applications of simulation and delve into why this field is becoming increasingly important in our complex world. Stay tuned. Welcome back to the Deep Dive. We've gone through like the basics of simulations, explored different types, and even dug into specific models like queuing systems and the cobweb model.
Yeah, it's been a real journey through the virtual world.
It has. But before we wrap up our exploration, I want to touch on something super important that we haven't explicitly talked about: the experimental nature of simulations.
That's a great point. Simulations aren't just about building a model and letting it run. It's about using them actively as a tool to explore and to discover things.
It's like having a virtual lab right at your fingertips, a place where you can test out your hypotheses, tweak variables, and see what happens without having to worry about messing things up in the real world.
Exactly. It's a playground for like what if scenarios. We can ask things like, what if we increase the arrival rate in this queuing system? Or what happens if the demand for this product suddenly drops? And the simulation can help us visualize those potential outcomes.
It's like a crystal ball. But instead of magic, we're using data logic and computational power to make smarter decisions.
Precisely. And just like in any scientific experiment, it's important to approach simulations with a systematic mindset. Like we need to define our objectives, design our experiments carefully, and analyze the results rigorously.
So it's not just playing around with the model.
Yeah.
It's about using simulations to get real insights that can guide our actions in the real world.
Absolutely. For example, if we're simulating traffic flow in a city, we might run multiple simulations with different traffic light timings, road layouts, or even like introducing autonomous vehicles.
And by comparing the results of these simulations, we can see which scenarios lead to smoother traffic flow, less congestion, and shorter commute times.
Exactly. Simulations give us the power to test those what-if scenarios and evaluate different strategies before actually implementing them in the real world, which can potentially save time, money, and resources.
This highlights a really important point. Simulations aren't just about predicting the future. They're about understanding these complex systems, exploring possibilities, and ultimately making better decisions.
You nailed it. In a world that's becoming more and more complex and interconnected, simulations are becoming a really valuable tool across so many different areas.
Well said. This deep dive has taken us from like the basic ideas of simulations and systems to the nuts and bolts of different types and models. We've learned how these virtual worlds can give us incredible insights into how the real world works.
It's been great exploring this fascinating field with you, and I hope our listeners have gained a new appreciation for the power of simulations.
Absolutely. And to our listeners, thank you so much for joining us on this intellectual adventure. We hope this deep dive has sparked your curiosity about simulations and their potential to solve those real-world problems.
Before we go, I want to leave you with one last thought. Think back to those cobweb models we talked about earlier, the ones showing the dance between supply and demand. What other real-world systems out there have those same kinds of fluctuations and feedback loops?
That's a great question to think about. You might start seeing cobwebs everywhere you look, from the stock market to like ecosystems. Who knows, maybe someday you'll be building your own simulations to tackle those complex challenges out there.
Until next time, keep exploring, keep asking questions, and keep on deep diving.
This is the Deep Dive signing off.